Hello, welcome. Hi, Billy. Welcome to McNeil Hall. Welcome to Zoom. Thank you, everyone, for joining us here. My name is Aidan O'Connor. I'm director of the Goldstein Museum of Design, and it is a treat for us to have our colleagues speaking for us and sharing their research for our public audience. This is the first public program related to our current exhibition, which is called Illusive Objects, which is in the gallery upstairs. If you haven't seen it, you can go see it after the talk. Thank you to our student worker, Nee, for pitching in and keeping the gallery open for us. And if you're joining us on Zoom and you haven't seen the exhibition yet, it is on until July 2nd. This is a collection-based exhibition where we're exploring the pleasures and pitfalls of elusive objects, things that are not as they first appear. I've been so excited to follow from somewhat of a distance this research that you've been doing with the Digital Ceramics Lab. But the College of Design is split across two different campuses. So it's really nice to have this opportunity to bring our areas of the college together. And I just want to highlight, while I have you, after this talk, we do have a few more events coming up, also in conjunction with this exhibition. We have a webinar on Monday, a few days from now, looking at the history of camouflage with Charles McFarlane, a fashion historian who's based in New York. Jean McElvain and I, who co-organized the exhibition, we will be having coffee with anyone who'd like to come join us in the lounge outside the gallery. And then on June 2nd, we're hosting Amy Lagos, who's a co-founder of the local wallpaper company, Higgy & West, and that's in partnership with AIGA Minnesota. And then another partner event we're hosting with Docomomo, Minnesota, is looking at an exhibition that was at the Museum of Wisconsin Art, where lost Frank Lloyd Wright designs for furniture were fabricated and put in conversation with historic objects. So some of these are touching on themes of optical illusion or reproduction. These are all coming out of the ideas of the exhibition. I've been hoping for the right opportunity to host this kind of talk and thought that a nice connection is that these are pieces that we just might not understand when we first look at them. They're not necessarily deceptive or trying to fool us, but there's something more than what meets the eye at first. And so with that, I'm just very happy to introduce our colleagues, and you will kind of give a better introduction, but thank you so much for coming. And that's all. Thanks. Thanks. Okay, let's see here.
Okay, hi everybody. Thanks so much for joining us today. I'm Molly Reichert. I'm an associate professor in practice at the School of Architecture and a partner in the public art collaborative Futures North. I'm going to introduce the three of us and then talk about the plan for our talk. So my work investigates the intersection of digital fabrication, material systems, and public engagement, particularly the integration of computational design and robotic fabrication with traditional ceramic reproductive processes. Jessica is a registered landscape architect and an assistant professor in landscape architecture. Her work investigates landscape change over time, hybrid representational strategies, and explorations into earthen and bio-based materials. And then May Hwang is an assistant professor in interior design, and her research focuses on material degradation and develops a framework to design for the end use so that material breakdown becomes a deliberate, productive part of the architectural process. We have a slightly meandering talk for you today. It covers our journey establishing a digital ceramic research lab, our respective material research practices, our grant-funded research initiative, Ecosystem Shifts. So before I jump into the lab, it's important that we first understand what is 3D printing. 3D printing is an additive manufacturing process that slices a digital model and using an extruder on a robotic gantry, prints it layer by layer, often in PLA or ABS plastic. In our school, students use a 3D printer to prototype models for a semester course or an end of semester review. The models, because they are plastic, then last until the end of time. 3D printing is valued in product design and prototyping for its speed and precision, but rapid prototyping in plastic inevitably generates waste that ends up in the landfill. So how is clay printing different? On the left, we can see there are 3 forms of plastic 3D printing: the precision and structural gymnastics it allows. On the right, the model that we printed in low fire red clay, and I'll say the imprecision that it allows. Clay is responsive to gravity, humidity, and pressure. It has emergent possibilities. Often we feel the material has its own agency, and we're just along for the ride. Unlike plastic, unfired clay can be reconstituted and printed again, making it a beautifully circular material in the prototyping phase. So what other materials can we print with? We are working within a much larger context of designers experimenting with additive manufacturing. So Hand and Machine Lab at the University of New Mexico is exploring biomaterials like orange peels, eggshells, and leaves. Emerging Objects at UC Berkeley, which consists of Ronald Rael and Virginia Sanfratello, 2 of my mentors, have experimented with wood waste, rubber, and wildfire ash. And then Rael Sanfratello also have worked at more of an architectural scale, creating Casa Covida during the COVID pandemic. And then there's also Columbia's Natural Materials Lab, which has developed digital earthen tiles printed from fiber and earth material. So now we'll get into our digital ceramics lab. In 2024, Jessica Daniel Keefe, our colleague in computer science, and I received a College of Design Digital Design Center grant to launch the lab. We started in a closet next to the metal shop in Rapson, and 3 years later, we've established a space in Rapson 11. And we share this with other faculty doing similar research. I also teach an undergraduate seminar connected to this research. Here's a diagram of our PotterBot, which is our ceramic 3D printer, and it is strangely high-tech and a low-tech piece of equipment. Oh shoot, I don't know if I can activate the video here. Do you know how to do that? Oh, nice. So just so you can kind of see it in action, it's really quite a rudimentary machine. The way that our machine works is that the extruder moves up and down in the Z direction, and then the bed moves in the X and Y direction. And then there's a machine on the top of the extruder that kind of determines the rate at which the clay is being extruded. So our initial work explored the printer's formal possibilities and constraints. Rhino 8 and Grasshopper paired with a PotterBot 10 Pro let us design complex, non-repetitive geometries impossible to design with traditional methods. This is an example of a Grasshopper script. It's a visual programming language that lets people engage with parametric design without needing to know how to write code. And then this is a really simple piece of that script, so I can kind of walk you through how parameters and components work with one another. So this is simply creating a box that's then contoured or sliced. So you can see here that rectangular kind of component in the middle is the rectangle component, and we're plugging into it where it's located at the plane and the XY origin, its size, so it's 10 by 10. And then we're extruding that rectangle in the Z direction in 10 units, so then it's a 10 by 10 cube. And then here we're just adding contours in the Z direction at a rate of 3 in 3 units. So then this is the resultant, what comes out of that code. And essentially this is a toolpath that will then print with a 3D printer. And then this is translated into G code, which is a series of coordinates or a script that tells the printer where to stop, start, move, and extrude. So as I mentioned, clay printing is wildly different from plastic. Plastic printers heat the material, clay printers don't, so it doesn't rely on the heat for the layers to adhere to one another. So there are unique constraints such as steep slopes fail and the tall objects wobble if the base isn't stable. We tested many variables in that first year when we established the lab: materials, speeds, extrusion rates, layer heights, forms. And there was a lot of failure in these tests that produced really beautiful emergent effects that quickly became our favorites. So here are a few more failures from those early days in different materials. And you can see we have a few failures up here that I encourage you to check out after the presentation. Clay's plasticity allows for unique forms, but printing a point or a line out in space, you can create these droops because the clay responds to gravity. Forms that can't be computationally derived to respond to attractor points and other parameters. So again, these really nice emergent qualities come with the material. And then something else that we did that first year is that we were really interested in less extractive, hyper-local material sourcing. So a friend in Ely, Minnesota, with a property rich in clay and a bobcat allowed us to harvest some on his site. We brought it back to the Twin Cities. We ground it, we sifted it, we added sand from White Sand Beach as temper, and a very labor-intensive process that only lasted a summer. But we're thinking about picking up that thread again in the coming years. So this is an image of that Ely clay in its unfired state, and you can see that it's a really beautiful gray-green. And then we fired it to a full cone 4, which is like a real, it's a real usable clay. And it became this really deep reddish brown with an incredible luster, likely from the white sands that came from White Sand Beach. We have samples here, so again, take a look. Okay, so now I will talk briefly about a couple of previous projects to show you what we bring to our current collaboration and kind of how we landed here. So 3 years ago, Jessica and I began collaborating on earthen tectonics, which merged my digital ceramic work in parametrically designed CNC routed slip cast systems with her CNC routed rammed earth systems. So slip casting, for those of you who might not be familiar, is a ceramic reproductive process where you take really thin ceramic slip and you pour it into a plaster mold that absorbs the water, leaving a solid clay layer that hardens into a final shape. So it's very thin and delicate. And then rammed earth compacts damp subsoil as a stabilizer in layers between formwork that create dense monolithic walls. We created 2 forms, concave and convex, thinking about how they might collect and shed water. We modeled them in rhinoceros, milled the negative forms in plaster, and then poured the slipcast modules and then rammed the rammed earth modules. Another very labor-intensive process. We're kind of into that, turns out. We incorporated native prairie seeds into our material mixes, hoping that as the modules degraded into the landscape, they would establish native species in the site. And we experimented with different rammed earth material compositions to calibrate their rate of degradation. Here's an aggregation of the slipcast and rammed earth tiles. The textural banding on the left is a trace of the CNC tool paths programmed in Grasshopper and carved into the plaster mold. The 24 modules were installed in September 2023 at the edge of a marsh in 4 locations, moving from submerged up the slope. By December 2023, after a very wet fall, many tiles had already disintegrated and were sitting in an inch of frozen water. By summer 2024, many were engulfed by emergent vegetation. The modules degraded at varying rates, and even after the first growing season, we began to see microecologies and microhydrologies shifting, new vegetation, leaf litter, and when you got close enough, insects.
So aligning with Molly and Jessica's research, I've been exploring the concept of graceful decay on the other side through concrete material. While traditionally defined by its permanence and rigidity, concrete material is inarguably material that responds to the passage of time. So I'm challenging the architectural obsession with immutability by intentionally designing for the end of life, creating structures that embrace natural weathering rather than resisting it. Concrete provided the ideal medium for this because it possesses the necessary structural stability while also showing the inevitable wear and tear over time. So I developed these experimental bricks by applying the principles of enhanced weathering, which is a term used for nature's own carbon capturing process, and that accelerates the mineralization. So for example, turning into stone, so it turns CO2 into stone. And it's called an enhanced weathering in science. By integrating biochar, plaster, some of the materials that Jessica and Molly has already used with adjusted calcium oxide level, which is the key element that allows a material to capture CO2 better, I created a material recipe that goes beyond just mere durability. So the goal here is a system that does not simply endure, but rather a material that actively sequesters carbon as it degrades, effectively transitioning from structural building block into carbon sink as it reaches the end of its life cycle. So while I share a material first approach with Molly and Jessica, which is very similar, my work takes a bit of a distinct departure into the realm of controlled lab experimentation. When I conduct experiments like this, I try to isolate variables, changing one element at a time, just like a scientist would do at a science lab. And when I iterate and make my design choices, this rigorous and iterative approach allows me to kind of rationalize my formal decisions and provide the empirical proof of the design process, as well as look at the material transformation through those eyes. This is my initial testing at SAFO, St. Anthony Falls Laboratory, which was critical for calibrating this methodology. By exposing brick samples to CO2 infused water, so this machine is called Rainmaker, and I fused CO2 in it to create a controlled apparatus, and I was able to track exactly how the form reacts and changes to an environmental stressor. So you can see that on the top graph, there are actually two lines. It's supposed to overlap with the initial status versus when it was rained down with the CO2 rain. Although the CO2 impact was very subtle in this early phase, the findings served as a vital proof of concept, at least to me. And by visualizing the material's life cycles through this concrete data, the project moved beyond the industry's focus on permanent fabrication. So to me, it introduces a new design language, one that prioritizes designing for degradation as a fundamental part of the creative process. For the next phase of this research, I scaled the project into a series of 60 experimental bricks, and they consist of 5 different compositions. They're tinted differently so that I can distinguish one from another. And I'm evaluating how these specific recipes influence carbon sequestration and durability over a set amount of time. So I tested out with 5 bricks, and they're all tinted differently, so they all are composed of different ingredients. And I tested this over this past winter through a 15-week winter time. All the samples went through winter weatherization, and the sequence you see here from week 1, scan 1 to scan 8, is captured via gigamicro imaging, and it tracks the exact same coordinate on the brick surface in 2-week intervals. So 2-week intervals, 8 scans, so that's approximately 15 weeks. And while some images appear darker than the other due to moisture level at the time of capture, the high resolution detail allows us to observe exactly how each unique recipe weathers and mineralizes under stress factors. So this one in particular is a blue brick, and it consists of Portland Portland cement as a base, a bit of CaO, calcium oxide, and biochar. This one is a purple brick, and it consists, every brick has Portland cement as its basis, and this one has biochar and plaster and CaO. This one is a red one, has cement, CaO, and plaster. And you can see that on this one, there was a drastic change after week 4, which is when the surface completely fell off and started to crumble. This is the yellow one with the most CaO ratio. So in theory, this one is supposed to capture CaO the most. And this is the green one with just plaster and cement. And so as you can see in these images, each recipe is performing differently, with the bricks displaying distinct degradation patterns based on their composition. So this is a critical discovery to me. It proves that the material to mineral, so material to stoning process transition isn't just random, but it's something we can actively design and tune. So ultimately, this project is more than just bricks. It's about creating a new toolkit for the future of architecture. And by understanding how these material recipes behave, we can start to design buildings that actually respond to their environment. So imagine a dome like this designed specifically for its location. The base could be built to stay solid and strong, while perhaps the upper shell can be designed to slowly transform, perhaps having more pores over time, absorbing carbon and healing on its own over time. So perhaps turning it into a more open dome in the future. Working like a scientist has changed how I think as a designer. By testing one piece at a time and looking for hard evidence, I can now measure it, and more importantly, design with the intent of predicting exactly how a building will age over time. So to speak, I try to embody what it truly means to be a sustainable designer. I believe the real value of this work is the bridge it builds between a lab and a studio environment, the design studio. It moves us toward an evidence-based design where beauty and environmental function work together perfectly. And as I said, this is my proof of concept that we can build structures that are as bold and beautiful as they are good for the planet. All right, now I'll move on to our current project that we're all working on together. This is where this was a perfect time for me to meet with Molly and Jessica to think about what are some of the impacts we can create with these clay modules. So first, I'll talk a little bit about the variable firing and degradation experiments. A very significant piece of our research explores variable firing techniques where we fire prototypes to sub-vitrification temperatures to test material temporalities. And we hypothesized that the kiln firing regimes could be calibrated to encode time scales into these materials, where some would degrade over a growing season, whereas some will degrade over a couple of years, and some not at all, depending on the temperature and vitrification amount. So we conducted a series of experiments to evaluate the durability and permeability of prototypes under controlled aquatic conditions. The first test submerged simple prototypes fired at sub-vitrification temperatures ranging from 700 to 1200. You can see the bottommost is 700 and the topmost row is 1200 degrees. We used the results to narrow in on a range of potential firing temperatures. As you can see, many prototypes disintegrated, especially the ones on the lower temperature, disintegrated too quickly for it to be useful for landscape intervention, so we discarded it. We then moved to more complex forms fired from 950 to 1250 degrees. And we speculated initially that the woven forms with more surface area will degrade more quickly than the straight forms fired to the same temperature. And as we do this, we want to document it, right? So, we're all designers. So we are doing imaging analysis to quantify the material properties and changes to the clay fired to each particular temperature. So this is the apparatus we set up at SAFO, St. Anthony Falls Laboratory. In our laboratory experiment, we are aiming to understand the role of varying water levels on the modules and material integrity. So the test simply replicates how a stormwater pond functions. They fill rapidly during stormwater events, as do real stormwater does. And then they slowly release water to downstream water over a period of 48 hours. And that's exactly how a stormwater behaves. The top image shows the low water level. So that's when the water has already gone down to downstream level, where the pond might be on a typical day, while the bottom image shows the high water level simulating a water event. So as you can see, one module, the one on the bottom, is always submerged. The middle one is always partially submerged. And the top one is only submerged and wet during stormwater events. So we currently have 2 fish tanks set up with pumps to fill and release water each week. We also have cameras for time-lapse setup for documentation, as you can see in this image, and a webcam so we can monitor the experiment from afar. We're currently running the first experiment on modules fired to 950 degrees, and with 2 more coming scheduled to test 1100 and 1250 degrees firing temperature modules. We started this process in early March, and we have completed 6 weekly simulated rainwater events to date. And although the water levels recede within 2 days, we do give it perhaps 5 more days for the top module to completely dry before starting the next simulation. And antithetical to our initial hypothesis, the street form module broke down much faster than the wavy form. And it became much more quickly, became brittle and showed cracks by week 3, whereas the wavy form only began to show cracks at week 7. An equally interesting finding was that the modules subjected to continuous wet and dry cycles, so the ones on the top, became brittle much sooner than those that remained moist the entire time. So this suggests that for a specific, at least specifically for clay materials, maintaining a certain level of moisture is critical in sustaining structural integrity. This image shows the apparatus from the trail camera taken just yesterday. You can see that the top ones, both for the wavy one and the straight one, were the most susceptible to breaking.
Oh, thank you, May. I am going to shift to talk about our ongoing research project, Ecosystem Shifts. The 3 of us have been ongoing with this a couple of months, moving from design and now into some material testing. It's supported by a Mississippi Watershed Management Organization planning grant and the College of Design. I think also KDI, Kusky Design Initiative, has supported this project as well. So we're super grateful to all of the support we've had so far. Our core team includes landscape architecture, interior design, faculty members in collaboration with researchers, stormwater engineers, again at SAFL, and our community partners at the City of Minneapolis Sewer and Water Division. So we are continuing with additive manufacturing or 3D printing and parametric design. We're starting to develop degradable modular 3D printed clay units that facilitate resilient biodiverse ecologies and impaired aquatic ecosystems. As a collection, these modules form a type of ecological infrastructure that degrades over time, and we're hoping this might start to improve water quality, capture sediment, stabilize slopes, and support emergent vegetation. By positioning clay as a living interface, this project seeks to catalyze a temporal infrastructure that supports emergent degradation and decay as an alternative to kind of a standardized inert infrastructure. So as May kind of alluded to, we are interested in working in stormwater ponds in Minneapolis. We have over 20 large urban stormwater ponds. These are designed to filter and slow down nutrient and sediment-rich urban runoff, allowing cleaner water to flow out to the larger Mississippi River watershed and our other kind of connected watersheds. So these ponds are really interesting because they're continuously monitored by the City of Minneapolis Public Works. So each pond has multiple years of data on sediment load, chemistry, water quality and flow, and soil characteristics. So these ponds will start to provide a useful test site to understand how our ceramic units as a form of regenerative infrastructure could interact with local ecologies and perform in real-world conditions. So as kind of alluded to, these ponds function by directing stormwater and urban runoff, which have a high level of pollutants and contaminants like, well, garbage, pesticides, road salt, and fertilizer, channels via underground pipes to these stormwater ponds and basins. So they're sized based on the watershed, so how much water is being collected, and fill pretty rapidly during storm events and then drain slowly over 48 hours. The ponds are kind of sized as well for the contaminants to settle to the bottom of the pond, allowing cleaner water to be released to downstream watersheds. And in Minneapolis, these are urban lakes or creeks in the Mississippi River. The stormwater ponds are really highly engineered basins from everything with precise slope angles, dimensions, soil characteristics, and drainage infrastructures. Vegetation lines the ponds, the edges, which stabilize the slope, uptake excessive nutrients, and provide habitat for invertebrates, birds, and other animals. However, these ponds often don't work as intended. So from our understanding of our local ponds and stormwater infrastructure, we have a threefold challenge. One is that they collect large amounts of sediment, which is moved from the urban areas and the erosive slopes, and they need to be dredged regularly to maintain function. They have high levels of nutrient runoff from lawn overspray, urban pollutants, and leaf matter, which starts to negatively impact water quality. And most ponds struggle with invasive and aggressive vegetation, which overtake desired aquatic and semi-aquatic species. So the high levels of sedimentation in particular impact pond performance, clogging infrastructure inlets, and building up along the basin surface. You can start to see that in the orange on the diagram. Invasive species shown in pink start to crowd out desired species that might provide habitat and food for resident non-human species. And then in green, the high levels of nutrients, phosphorus and nitrogen cause algal and cyanobacterial blooms, which impact the water quality of discharged stormwater that is meant to be kind of cleaned as it is released downstream. So through this project, we were looking at a nearby stormwater pond, the 25th Avenue stormwater pond right on the edge of campus, that struggles with these three main challenges. The pond has sufficient data collected by our community partner on water quality, quantity, turbidity, sediment collection, nutrients and pollutants of concern, their management practices and frequencies, so how often it's dredged, and they also have really comprehensive base maps and other technical drawings for us. So it's also one of the smaller scale ponds in the Mississippi River watershed. Some of these ponds are really, really large. So thinking about, I don't know if you'll see some of our prototypes, like how do we intervene meaningfully in these systems to make the most impact? So we've kind of started this level of site analysis, creating base maps and diagrams to describe our pond's characteristics and challenges. This drawing in particular starts to map locations of sediment collection shown in the kind of red and green colors, and deposition, their maintenance procedures, pond grading, and stabilization methods and materials, which are kind of the notes and the diagrams on the side. This drawing will be used to inform the locations of our future installation and what function they might need to perform. So what are the challenges we're addressing, and where does the pond kind of struggle from these the most? As well, we've continued to develop formal potentials utilizing our 3D printer to understand how voids, ridges, textures, and droops could start to support our vegetation, promote microbial colonization, collect sediment, and perhaps filter water. This matrix describes our initial exploration of formal typologies that will get combined with each other to develop more formal or more complex geometries. It's organized along a gradient where the left-hand side indicates, less formal manipulation, such as really low porosity or low amounts of surface texture, and the right indicates a more extreme expression of these characteristics, such as highly degradable or highly woven. We've done a lot of design prototyping with the 3D printer and our unique grasshopper definition. I think we have a very similar one. I'll show Zoom so you can get a sense for the size and scale. A very similar one here, looking at a form with highly woven and porous surfaces that might start to do these functions as we intend, with a central opening to start to support and shelter emergent vegetation. Each of our prototypes maximize surface area and porosity using droops, weaves, surface textures, which are inherent to the clay material in the 3D printer, which Molly mentioned. As we've been designing these prototypes and working through our material degradation experimentation, we've developed a series of conceptual renderings that begin to speculate on the temporal material qualities, vegetation growth, and water quality improvements of a potential degradable installation in a stormwater pond. We've taken the matrix to kind of test how specific formal qualities might start to come together in this module design. So at installation, the modules are embedded into the slope of a stormwater basin across varying water levels. As in our experiment, some are always submerged, some are partially submerged, which might start to suppress invasive and undesired vegetation species and become fully submerged when the basin is full. Others are never submerged and they start to act as slope stabilization, vegetation suppression, and a method to establish some of our desired invasives or our desired vegetation species. So as an installation, they also start to provide visual interest, which might signify an intervention to passerbys. We're also really interested in how this work can be visible and legible to people in the community. So over time, modules might start to degrade, releasing their embedded seeds, providing a scaffold for emergent aquatic vegetation, stabilizing our slopes and capturing sediment in the pond water. We imagine the modules degrading at our varying rates from a growing season to maybe never, and some pieces could essentially be a permanent infrastructure. So upon the complete degradation, there's little left of the design modules where they've acted as an ecological infrastructure or framework to establish some kind of unknown future. They've essentially disappeared and vegetation and other systems take its place. So we're looking at this work as extending the lineage of different additive manufacturing from ceramics and experimental materials into landscape, well, I don't like this word, infrastructure and design degradation, starting to draw inspiration from biomaterials, 3D printed forms, and ecologically active soils. So this is our early stages. We're starting to test and think about how these 3D printed forms could start to create these conditions for rooted vegetation and microbial colonization. So that's kind of where we are with this project. We have a lot of next steps. We've been starting to develop more intentional and site-specific forms for vegetation establishment and slope stabilization. We have an experiment that's being designed and constructed at St. Anthony Falls Laboratory to actually test some of our next round of prototypes in a slope outside with the kind of rise and fall of water levels. And then once we've gotten a sense for how these things can perform with freeze thaw, with vegetation growth, and over an extended period of time, we'll move to the small scale installation at our 24th Avenue Stormwater Pond, and we can start to assess and monitor real world impacts using quantitative metrics. So kind of drawing from some of the experimentation that May has talked about and the City of Minneapolis's data that they've been collecting. So kind of bringing those two things together. Yeah, I think that's all we have. Thank you so much for listening. We'd like to open it up to questions, thoughts, or maybe any ideas that you have.
Right. This is why it's so cool to be in a museum, a design museum at an R1 university, because we get to see this research happening before our eyes. I'm wondering, can you talk a little bit about the relationship with the community partners that you mentioned? So this kind of research project, are you identifying the need and then you're finding the support? Are they identifying the need and then coming and looking for the right partners? How does that work?
Oh, that's a really good question. I think we kind of came together out of this interest in stormwater, and working with our partners at the City of Minneapolis have identified these issues. So we have identifying the issues for the stormwater ponds. So they've really driven us to what kind of issues we should look at, where we should think about intervening, in the particular ponds that have the greatest concern, kind of concern for these challenges.
Y'all can hear me. Oh, for Zoom. Hi, Zoom. Earlier when you were showing like the slides of the testing on what firing temperatures, was that in Celsius or Fahrenheit? Okay.
It's in Fahrenheit, yeah. So it's
Okay, so
very,
ex-
very low
Yeah,
temperatures.
extremely low. Okay,
Yeah.
interesting.
Higher than your oven, but
Yeah.
still not like traditional.
Yeah, not
ceramic
traditional
level,
ceramic. Okay. And then my other question was why 3D print these objects that are going to be as the storm water? Because that's like a really intensive process and they're like so intricate and beautiful compared to like the other processes they could be made.
Yeah, that's a really good question. We're constantly returning to that question ourselves. And what
This one works.
Okay, I think we're done. Oh,
Thanks. What the 3D printer allows us is endless customization. Thank you. I'm like, what is that word? Customization. And so we're allowed to make something very, very site specific. And even, specific to particular slopes along that site. The other thing that allows us is to make structures that are very, very porous, which in the end is really important for the work that we're doing. And the modules that we're making also have a lot of surface area, which in the end is really important also for this work. So these are all, in many ways, just what we're hypothesizing at this point. So we're figuring it out as we're testing. But it's a really good question and something that we're constantly coming back to, like, why is this method of fabrication consequential? And kind of TBD, to be honest. Want to add something else?
About vegetation.
Well, I was just going to mention maybe if you want to talk about vegetation, about the kind of like droops and weaves and some of those formal qualities and how we could think about those as not being just a decoration, but start to do things. So actually thinking about how form and function start to relate to each other. So there's some really interesting possibilities within that we're starting to pull apart and really make the 3D printer doing unique things for us.
I mean, we're also hypothesizing that. So one of the goals for using these modules is to be able to grow more native species within stormwater. And I highly hypothesize that those pockets and those weeds would allow for the vegetations to grow and adhere to better than just having like straight modules. And so I'm assuming that that would be a plus or benefit for our intervention.
This one should work now. Okay, thanks.
Lovely presentation. Thank you for review. As you picture the implementation, or as I picture the implementation of this and almost the messiness of putting it in there. I mean, I don't have a lot of knowledge of how typically that would be done, but I want to see it. And so I wonder, is it you three plotting them? Is there this anticipation that the soil is going to move around you? I guess, like, how sturdy do you picture? I mean, because you're kind of needing to map specifically where those go in order to, gauge that. And also, I guess the next question too is, will you have underwater cameras that kind of show, and how do you figure out exactly how much is degrading underwater?
Yeah, great questions. I was actually just in the lab today prototyping some things about how these things are anchored into the ground, right? And acknowledging that the soil is probably pretty squishy and soft. So how these things sit in the ground, how they're anchored in with the module itself, I think will be really important. We were looking at different ways of digging from like bulb planters, like with your drill, the augers, or like post diggers, and just trying to see like how we might use things to install different tools to install these modules, because it will be us, and it will be dirty and messy. So also thinking about what we can feasibly do in this first stage, because we will be doing a lot of the labor. So yeah, that is something we're kind of thinking about. And as we design the second round of prototypes, how they sit on the ground will be really important. Oh, sorry. Oh, documentation. Yeah. Underwater cameras. That'd be great. I think what we were just kind of learning more about how these ponds function is in the fall, like October, November, the pond levels are really low. So I don't know if you saw the sectional drawing, there's like a slope and then a bench and then a steeper slope. There's this bench that always has water, except apparently in the fall, because the water level gets lower than that. So if that's our lowest water, we'll be able to like get in there and actually document them. So I think there's kind of like seasonality, seasonality pieces will play into it of what we can assess, and other things that will just be like a kind of a surprise when we find them again.
I have a question. Thanks so much for the presentation. It was really interesting and provocative. When you were talking about your intervention in stormwater ponds, you were talking about the replanting of native plants. And one of the things that I think about with stormwater ponds is there must be a lot of mechanical filtration of it in order to remove toxins that have accumulated there. Other than the kind of plantings that you're doing, are you also thinking about the possibilities for this kind of intervention within that space to replace those kinds of mechanical filtration technologies as well as a more sustainable alternative? Because probably the mechanical filtration also is very kind of material intensive in terms of how you have to do it.
Yeah, totally. I think what's really curious about how these ponds function, it's a totally passive. The length of the ponds is specific. So when water enters the pond and kind of travels the length, it is long enough for those particulates to settle. So the pond itself is starting to do some of that work where other places might have like mechanical filtration. We are kind of going back and forth about how do these things filter water and remove some of those pollutants? Do they collect them? But then it kind of raises the question of, do they need to be removed, or are we creating another problem that needs to be kind of dredged in these little microsystems? So yeah, it's the filtering is a really interesting component. And I think kind of maybe utilizing both those inlets and outlets, and then the length of the ponds as like a settling strategy. I don't know where we're going. Yeah.
I can also add a bit to that. So it's not that we haven't thought about it. We are very aware that it has a lot of stormwater tend to have a lot of phosphorus, which is one of the major problems in stormwater. And so we did think about, we even wrote a grant that didn't get through, where if we mix in some iron in the clay, then it captures that phosphorus much better than any other material. And so we thought about perhaps, using that as a method to kind of filter through the water. But at the same time, this is when we go back to the scientific method of let's test one at a time, because if we do many things at the same time, we don't know what really was effective for us. So at this time, we're not so much focusing on the water quality remediation, but more so on seeing the vegetation growth and to test if our firing temperature and slightly scaling up would work for our intervention. Yeah, but it's on our radar.
You had mentioned that the soil, that like particulates that settle in the ponds have to be dredged periodically. I'm curious if you know like where that material goes and if there's any potential for like recapture and
Yeah.
processing of that? I imagine it's maybe a little unruly, but
Recapturing the material is something to print with, you mean? Or, yeah.
I mean, it,
With the minerals.
yeah, if there's any way that
Yeah.
that works back into kind of like the material
Yeah,
process.
it's something that we've batted around. It's funny that what we keep on running into with this work is that there's so many ways to think about it and so many ideas that we want to incorporate. and it's we've had to be really, really measured in what it is that we're studying because, like May said, it doesn't really work to have multiple variables when you're testing. So something we've considered but haven't really followed yet.